Hi, my name's Mark Dickson. I'm at the University of Auckland. Thanks for the invitation to talk on this topic of modelling coastal cliff erosion. I'm going to start by mentioning what I'm not going to talk about, which is the kind of short-term uh, cliff landsliding processes, an important topic. But here I'm going to focus on longer-term processes, coastal cliff and platform evolution over decades to thousands of years. And at this scale, it's not just the evolution of the cliff profile that it's important, but also the evolution of the underlying rock profile. So this is a shore platform we can see on the eastern coastline of New Zealand here. It's partially obscured beneath a sandy beach. Sometimes these platforms are completely obscured, but here you can see a little bit of it. And so the evolution of the cliffs also depends on the evolution of this shore platform, and I'll talk about that as well. I want to start by providing a little bit of context that won't be a surprise to many people that there are coastal cliff erosion problems in many parts of the world. I have examples here from California and Oregon, also the coast of Norfolk. And here are a couple of examples from New Zealand as well, Auckland and Wellington with cliff top properties. And the slide I have from Auckland also has a little graphic showing some mapping of the number of cliff top properties in 1950 and 2006. And we can see that not only is there an ever-increasing number of properties on the cliff top, as illustrated in the construction activity that we can see in this image, but people are building bigger properties closer to the edge. Cliffs are receding quite naturally, and so we're moving toward the receding edge, and therefore the erosion hazard is growing strongly through time. Beautiful European heritage towns have clung for many years precipitously to cliffs that have been often quite stable over these periods of time. And yet, as illustrated with this spectacular, so I'll turn that step down, this spectacular kind of video that many of you will have seen before on the hard rock cliffs of Cornwall, we can get spectacular catastrophic failure events operating over very short timescales. These cliffs could have been stable for very long periods of time and then suddenly fail. And it's noticeable in this image that there's not heavy rain on this day. There's not strong storm waves attacking the cliffs. And so we get some insight into the fact that the driving processes of cliff erosion can be decoupled in time from the failure events that actually occur. The cliffs of Sydney here, it's hard sandstone cliffs, but with spectacular storm waves attacking the cliff face. And an example from Claire Early's PhD work, again back in the UK, where they were able to document a really extreme storm during which cliff retreat was more than 100 times larger than the long-term average. So sometimes these extreme storms can drive really rapid cliff retreat. Sometimes the cliffs may retreat rather little during these events, and the failure could occur during a period of time in which the weather is really quite benign. So what are the challenges and opportunities for modeling coastal cliff erosion? We know that cliffs occur along more than half of the global coasts from Adam Young and Jessica Corelli's work. We know that many of these cliffs are urbanized. We know that there's important cultural heritage on many cliff tops and numerous asset classes. So therefore, projecting future sea level rise impacts must represent a key goal for us. But this is going to be a challenge because of slow and often episodic change. As mentioned in the last slide, there are lags often between process and response. And there's a sort of fundamental lack of preserved evidence on eroding coastlines. The evidence has been removed away, unlike depositional coasts, for example. And all of this sort of comes together to result in relatively limited physical understanding of coastal cliff erosion mechanisms, limited evidence of long-term coastal retreat rates with which to constrain our numerical models. And this is problematic because we know that the morphology of the cliffs and the shore platforms is an ambiguous indicator of the processes that have created those forms. As we'll see later in the talk, equifinality we know is a problem. Bob Kirk noted this difficult issue around morphology being an ambiguous indicator of process almost 50 years ago now. This problem is somewhat less acute on rapidly eroding coasts, and so it becomes useful to make a distinction between soft rock and hard rock coasts, in which the distinction is really down to the erosion rate. Soft rock coasts erode at a rate that's sufficiently large that we can use the historic record, historic photographs, for example, to give us coastal erosion rates, which we can use to help inform our models. Whereas hard rock coasts, it has been very difficult to get geochronological information out of these coasts that erode almost imperceptibly slowly over human time spans. This problem is becoming smaller, though, through advances in things like terrestrial laser scanning, also clifftop seismometry work. And what I'm going to talk about a little bit in this presentation, the use of cosmogenic radionuclides as a clock, some sort of a clock for long-term millennial scale erosion rates. And these types of tools are beginning to manifest in the models that we're using for hard rock coasts. So here's a list of soft rock coastal cliff erosion models. I have the full reference list available at the end of this presentation. There are too many models here for me to work through. I hope I'll be forgiven for kind of picking on one that I know a little bit more about, the Walkden and Hall model, but the kind of process response system that this model provides is similar in many respects to many of the other process response models, although you'll see that there's a large number of different types of models, including statistical models included within this list. But the Walkden Hall model, the SCAPE model, which I've also worked with quite a lot over the years, is characteristic of some of these other types of models, in which the intent is really to try and describe a broad coastal system. And if you look within some of these bubbles here, you'll see that sea level rise is sea level rise representation is provided, waves are described, the emerging coastal profile shape is described, sediment transport is described, and really the effort in a model like this is to actually describe the interactions between these different parts of the system that ultimately control system behavior. The driving equation for profile evolution, you can see, is dependent on the energetics of the incoming wave field, and you can see that there are a range of functions for the way that wave energy is distributed across tides and how those tides change as how the water level changes as the sea level rises and so forth. And importantly, you'll see this term you'll see this term in the model here as well, that's common to many of these process response type cliff erosion models, where you get the erosion rate through calibration via comparison with field data. So historic photographs, for example, can give you the coastal erosion rate over time. And therefore, the confidence in these models really comes from comparing the emerging profile shape with profile shapes measured out in the field. So as an example application, this is the coastline of East Anglia, the Norfolk coastline. It looks relatively simple in plan view at this kind of scale. But when you zoom in, you can see that actually the coast is really rather complicated because of the effects of engineering interventions over very long periods of time that have interrupted coastal sediment transport and coastal erosion rates. Yet with a systems model like this, it's possible to represent these types of interventions through time. And by comparing model outcomes with measured coastal recession data, we can give ourselves some confidence the model is doing something useful and use that as the basis to make some sort of statements about what might happen in the future under various climate change and coastal management scenarios. So soft rock models have advanced to a point that I think they can be useful for a range of coastal management applications. A recent approach, or relatively recent approach, employed by the USGS, led by Pat Limber, involves producing an ensemble of several model outcomes. I've highlighted in blue here some of the models used by Limber et al. In this study. And interestingly, all models used in this particular study, this is for the Californian coastline, predict a steady increase in soft rock cliff erosion rates with sea level rise. Notably, the Trenhale and the energy flux models predict a somewhat higher increase in coastal erosion rates because they're very sensitive to wave impacts on the cliff. And these impacts increase non-linearly with the sea level rise. I think this ensemble type approach has value and should be used more in the future. It provides an inherent way to outline the uncertainty within different models. It filters out some of the kind of noisy, unusual outcomes of individual models, but reinforces common model behavior. What about a more generalized framework for predicting the response of cliffs to sea level rise, not just soft rock cliffs? I think there's been some interesting work done by Andrew Ashton here, kind of leveraging some of the work that Mike Walkden and myself did some time ago when we used the SCAPE model once again to test a very broad model parameter space and investigate how the future sea level rise may drive increasing coastal erosion rates. Brooks and Spencer's compared the relationship we derived here with several others and found it to be useful. Andrew Ashton, working with us, then realized that it would be possible to kind of make this framework or make this relation more general to other types of coasts. So this one, the square root relationship might be expected to hold for sort of soft rock coastlines, for many soft rock coastlines, and negative feedback type relationship where the rate of future erosion will accelerate with sea level rise. But there are other types of coastline where we might expect the relationship to be quite different. For example, if there's very little resistance from the rocks, maybe sandy bluffs, for example, we might expect an instant response to sea level rise. Or maybe in hard rock cliffs, there may be some instances where we expect the rocks not to respond to sea level rise at all. The erosion rate in the future will be the same as in the past. In some situations, it may be even the opposite. Maybe we could expect to see slower erosion rates in the future under sea level rise potentially on limestone coasts where solution processes control notching, which controls the rate of cliff retreat, or maybe even on some coasts which are dominated by the wave impact regime, because if we flood cliffs with sea level rise, we may get more reflective cliffs and potentially sea level rise rates could actually decrease future erosion rates. So this kind of generic framework, I think, is an interesting one. Of course, the challenge becomes in understanding the value for M on different types of coast. So where are we at with hard rock erosion models? A lot of work has been done in this field. I point people in particular to Trenhale's recent review of hard rock coastal modeling. He makes the point that it's extremely difficult to convert energy dissipation rates, wave energy dissipation rates, into corresponding rates of rock breakdown. He makes a point that attempts to measure and quantify the driving and resisting forces that determine cliff erosion continue to be confounded by myriad factors that operate on complex rock coasts. So the models that we have remain highly abstracted in their physical description of erosion. Once again, I hope I'll be forgiven for sort of picking on a couple of models that I've been closer to. The work of Hiro Matsumoto, who did his PhD work with me many years ago now, and also the work of Martin Hurst, followed by Shadrick and others, using cosmogenic radionuclides. So let's start with Hiro's work on the rock profile model. Again, I'm not going to get into the details of this model. It very much follows the conceptual framing of Tsunomura, in which erosion occurs when a sailing force of waves exceeds the resistance of rocks. One thing I particularly like about this model is that it produces a broad range of profile shapes that we see out in the field environment. I like also that within this model, wave and weathering processes both compete and conspire. Weathering processes reduce the resistance of the rocks through time. The rocks are then eroded away by waves. So we can compare the relative importance of these processes through time. One thing that we note from this work is that similar profile geometries can result from a model parameterization that either results in wave-dominated environment or weathering-dominated environment. You can have a shore platform shape that's produced mainly by waves, or a shore platform shape that's produced mainly by weathering, and they look almost the same as each other. So this is a classic kind of geomorphological equifinality problem, and you can understand why field workers for many years may have argued about wave and weathering process dominance, because it's quite possible they're looking at two quite different process regimes producing very similar morphological shapes. So how do we grapple with this type of situation? I think a very promising development within this field are attempts to constrain hard rock coastal evolution models with cosmogenic radionuclide data. So following the work of Ragard and Hurst, we know now that we can use in situ cosmogenic radionuclides like beryllium-10, for example, as a geochronometer of coastal landform development through time. I knew I was going to have problems saying that word. A chronological measure of retreat over millions of years. And what becomes very interesting is that by creating an environment in which we can explore the rock profile model with a wide variety of different parameter states, we can iterate through time and test these parameters to see which combination of parameters is most likely to represent the rock profile, emergent rock profile shape best. So this Markov chain Monte Carlo optimization scheme reveals the most likely model parameters that have produced a particular profile shape. And I think this is a very important way for us to reduce equifinality problems. I think this is very nicely described in the work by Shadrick et al. It's interesting that then extending this work forward suggests that coastal erosion rates are primarily driven by sea level rise over millennial timescales, and on the basis of that, they were able to make predictions that the rate of cliff retreat in the future may increase by an order of magnitude, driven by the current and future accelerating sea level rise that we observe. I think one cautionary note in relation to this work is to say that our rock coast evolution models over decadal scales are still not sophisticated in their process representation. So one way we've been trying to address this point in recent work led by Hiro Matsumoto, again, is to explore how wave breaking patterns are likely to change as sea level rise increase, and how breaking, broken, or unbroken waves may exert force on the cliff face under different sea level rise settings. As a result of this work, we sort of concluded that existing limitations in our model process representations prevent accurate projections for hard rock coasts over the next century. And we explored a broad range of profile shapes in Auckland and San Diego, also an example from the Vale of Glamorgan in Wales here, and examined changing wave breaking patterns with a given sea level rise, but ignoring any morphological response. We see that elevated shore platforms, like we see in places around Auckland, see big increases in wave breaking impacts with sea level rise, whereas lower shore platforms, a couple of examples here from San Diego and Auckland, actually can see a decrease in the amount of wave breaking impacts over time as sea level rise starts to flood the cliff and wave energies reflected. So coastal erosion rates could potentially decelerate with sea level rise on some of these coasts. The Vale of Glamorgan and other sloping platforms show increased broken and breaking wave patterns over time, which is generally consistent with the work of Shadrick and Hurst and others suspecting an increased erosion rate under sea level rise. So cliff retreat rates are generally expected to increase as future sea level rise accelerates. However, changes in cliff front waves in response to future sea level rise are complex. We think it's unlikely that future cliff erosion will homogeneously accelerate with sea level rise. So just to conclude here, in terms of the way forward, I think ensemble soft cliff erosion models are useful, should be explored further. I think the work with Monte Carlo Markov chain modeling to constrain hard rock models with cosmogenic radionuclide data is very important and will be useful in the future. I think there's an important need to increase our mechanistic understanding of fundamental erosion dynamics. And just a shout out here really for some current work looking at notching through numerical schemes, some work led by Maria Napoli in Italy here, and also Yashong Shen working with us here in Auckland doing laboratory work. And I couldn't work through all of the models that exist out there in nature, but here's a collection of references for those who are interested in learning more. Thank you.